To a new lecture. In this lecture we're gonna see about input, output, and also interrupt. So input, output, we're just gonna see mode 0 input, output. So let's begin. Before that, as usual, input, output, and memory. So for memory we have FFFH till, from 0 till FFFFH, meaning that we have 2 bytes, also known as 16-bit. So in this case, IO or over M should be equivalent to 0, which means that memory is in active flow and IO should be off. Whereas if IO is on, then we have 00 till FF, which is equivalent to 1 byte, or known as 8-bit. Okay. Now, for 8255A, or we call it 8255A peripheral interface, we have 24-bit digital IO, 2 times 8-bit unidirectional port. Unidirectional mean it only can travel in a single direction, whereas bidirectional mean it can send and receive. Okay, and bit set, bit reset on 8-bit. So we have port C. So we have port A, port B, port C, and also control register. So what does it mean by base address plus 0? For example, if the question gives you base address 80H, in most cases it's 80H, then in order to activate port B, we need to name it as 81H, or if you want to use port C, it's 82H, or if you want to use the control register, it's 83H. So the base address plus by this 0, 1, 2, 3 will reflect on the port A or B or C or control register that you want to use. Now we use control register to use the mode word. So what is the mode word? Before we continue to the mode word, this is a diagram that you need to understand. So in this diagram we are given that group A and group B. So the question could ask or could tell us that we need mode A in group A in mode 0, group B in mode 1. So this is the mode selection. Okay, so the easiest way to remember this without the diagram is this: 1mm AC MBC, or you could remember this in any mnemonic that you want, but this is the easiest way that you can remember, whereas this is always set to 1 and these 2 is for mode. If mode 1, it's equivalent to 0 1. If mode 2 is equivalent to 1 0, and mode 0 it is equivalent to 0 0. A means if 0 it's output equivalent to O, if input it's 1 equivalent to I. So this C is high C, and this M is for the group B, and this B is as usual same as A, and this is for the lower part. Now if we look at an example, they say that write the initialization code for 8255A at base F0. So automatically we know that this would become F0, F1, F2, and F3 for control word. So they say that both groups should be, A and B should operate on 0. So you know that 1 M M A C B C. So the mode is said that both group is in 0. So 0 0 and MBC 0. Then they said that input port, so A is input and port B is output. So then they say upper is output, so this is upper output, and the lower is input, so this one is same. So we will get this number which translate to 9 and 1. Now 91 into A, and that is outputted into the control word. So as usual and as said in the previous lectures, we need to move to the accumulator, then only we could move to the input or output. So in this case the control word translate us to 91H. If you ask whether you want to write in byte, you could also write it as such. Okay, so you could write it in a byte or you could write it in a hex. So this is how you write it. Just to remember, the control register is as such with the base address that's been given. Now another practical example is, so this is in mode 0, which is quite easier. Then they say they have these 12 switches. Okay, So mode 0 means we will write this 1 MMAC MBC. So this one is 1. So mode 0 means everything is working in 0. Now PA, so the A is now a output. So A is output. The C, high C, so this is the high C. The high C is also output. Now this is input and this is also input. So the balance in input, which translates us to H3. Okay, now here we know that it translates to A3 too. So first of all we need to make it to control word, which is 83 into A and into F3, which is the control. Now F1 is our in, so the in F1 is actually translate to out at F2, which is A is equivalent to the B is F1, A is 0. Yeah, so A is equivalent to base address plus 0, which is equivalent to F0, whereas B is base address plus 1, which is F1. So in this case B is working as output, so F1 is our out, and A is working as our input, so A1 is our output and B1 is our input, so F1 is our input. So here F1 is the input, B is our input, and A is our output. Now in the second case, our C is equivalent to F0 plus 2, which is equivalent to F2H. Now here is a special case. F2H for us is the lower byte is actually the input and the higher byte is output. In this case, our lower byte could be 000111. So if we translate this into out, it doesn't actually prove anything because our output is actually in the higher byte. How do we do this in the higher byte? We need to rotate it to the left. Before we rotate, we have this N. Why do we have a N? And we are doing the N logical operation with 000F means 0001. Why do we do this? The resulting would be 000111. If the input was 1010, the result would be 1010 as well. We are doing this in order to clear the input. Maybe it was 1010. So this was our input for C. We want to clear the output of C before we send this input to the output. After we do the AND logical process, we would get a result of this. So we will do RLC 4 times, which makes us this 4 bit to move. So technically we have this. So this will go here, go here, go here, go here. So this will go here, 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 here. So the resulting would become as such, where this is the output, and when it's output, it's going to the output. The input from here is now reflecting in the output. So the AND is needed to remove the unwanted crabs. Crabs means unwanted stuffs. Okay. Now, what is the difference between mode 0, mode 1 and mode 2? So mode 0 doesn't have handshaking, but mode 1 and mode 2 has. So direction, mode 0 is only one way, mode 1 is one way, mode 2 is two way. Now the ports allowed are mode 0 has every ports allowed, mode 1 only A and B, and mode 2 only has port A. Now why is this important? To limit and unlock the capabilities of port A and port B. If you are using port 0, you need to have A, B, C. If I only want to use port A, I don't want to use port B or C, I will be using mode 2 to only take port A, which I don't care, and I ignore about port B and port C here. Now what's handshaking? Handshaking is declared as a communication protocol used to synchronize a fast device like CPU with a slower device like printer or keyboard so that the data is never lost. So our CPU is running in gigahertz. Maybe our keyboard is running in megahertz. Now gigahertz is more faster than megahertz, so the data traveling could be missed. In order not to miss, we need to have handshake. By using mode 1, port C is handling the handshake. So what's going to happen is we have A, B, C. Assume A, B, C are each highway. So in this highway it's going in 158 km, but in C it's just going in 20 km. So our CPU is running in 158 km per hour, but the keyboard and mice is running in 20 km per hour. So in order to maintain the speed, in this speed they could transfer the data. In this bit, the data will be scattered over. So here is the usage of mode 1 and mode 2, where the deeper knowledge tells us that in mode 1 and mode 2 we have the OBE, acknowledge handshake, happening. Okay, now the next part that we need to know is interrupt. Interrupt actually does suspend program execution and instead execute a software module to service the event. So as an example, our processor is running in gigahertz, or our processor is running in some process. Now suddenly we are trying to connect a micro USB drive. So micro USB drive need to send the data in. In order to send the data in, it need to interrupt the process that's been running in the processor. So there is the word interrupt occurring. So the interrupt actually halts the process. Okay, so we have another term called ISR. What does ISR do? Interrupt service routine. It's actually a software module that processor executes in response to an interrupt. Okay, so for an example, if I have my MTK85 board, in that board I am running a simulation or a game. Now I have pressed a button to pause it. So while the pause button is executing, maybe I am doing a running LED light. So ISR is that. So the advantage of using interrupt is faster response time to external events, reduced overhead in the processor, improved system performance by allowing the processor to handle multiple tasks simultaneously. Now remember the example that I gave. I am trying to put a micro USB in it. Now imagine that the processor is not being interrupted, so I need to wait the processor in order to finish its process for me to plug in my micro USB. If I'm running a simulation that takes me 1 hour of time, I need to wait 1 hour just to copy a 2 MB file to my micro USB stick. So with the interrupt, I can just pause it, I can plug it in, I can copy it, and I can resume this video processing, which saves me time. So this is how it's gonna happen. Now for interrupt, we have the specific diagram where the normal processing is doing, then the interrupt occurs. So we save the maybe line 2000, 2002, 2003, and suddenly interrupt occurs. This 2003 is saved in the stack. So branch to ISR, we jump to the ISR may be located in 8000, then we execute the ISR, we retrieve PC from stack, which is the 2003, then we continue the process. Now it's going to be 2004, 2005, and so on. Now this is a interrupt table. Now in this table we know that these are the interrupt pins. So this is vectored and direct. So intar is vectored. Now this is maskable, okay, and trap is unmaskable. And we have the address for trap, it's 0024, it's static, and the priority is we given the highest priority to trap, and then followed by 7.5, 6.5, 5.5, and INTR. Now for an example, take 6.5, we need to find the address ISR, or take 5.5. So 5.5 times by 8 will get 44. 44 is equivalent to 2CH. How? 16 times by 2 plus 12. So 12 translate to C, and this is 2. So you need to be familiarized with the decimal to hex conversion. So this is how it works, and this is the table. So this is the decimal and this is the hex. So as said, 12 in hex is C. Okay, so 2, 16 and C. So for 5.5 times 8 is 44. 44 translate to 2CH. So the vector address ISR for interrupt 5.5 is 2CH. Now this is something that you need to know. Now trap works in a rising edge and high level. 7.5 works in a rising edge. The balance works in a high level, but INTR is vectored. So the only stuff that we can use in a program for hardware interrupt is 6.5 and 5.5, especially in a MTK85 board. Now we know that this is the hierarchy. So this is given the top priority, second priority, third, fourth and fifth. How does it happen? If a program is there and we have 3 interrupt and 3 interrupt occurring in the same time, we will give the priority to 7.5 first. But in this case, due to high level, we are just going to focus to 2 interrupt thing. So this is how you do the mask for interrupt. In order to do the mask, we need to know that which interrupt that we are trying to use. If we are trying to use 6.5, this is the mask that you need to use, and 5.5, this is the mask that you need to use. So if we translate this 0 0 0 0 1 1 0 1 for 6.5, so the balance for is everything 1, which means that we set the bit to 1. 7.5, 1 means mask, means we are not going to use it, we are going to use 6.5. so 0 means available, so 6.5 sits here, so we make it 0 as we are trying to use it, we make it available. 5.5 is a 1 here. Meanwhile, when we're trying to use 5.5, we are doing that 5.5 is 0 and 6.5 is 1. We are trying to use the one that we want to use. Okay, so these two numbers are something that you need to remember without any acronym or mnemonics. If you want to do a mnemonics, and it's depend on you. Now, a direct interrupt is equivalent to 60 states. Now, in a programming, so in this program, I'm trying to use 65 and also 75, where the ISR is 34 and 36. Do we need this? Yes, we need this. So we put the address and we tell that jump ISR. This could be changed to anything, jump interrupt 1, interrupt 2 or anything, but this ISR address need to be same. Now we see here we have 0 and 0 here, which means that 7.5 and also okay, technically here is an error. If they are trying to use 6.5, they should have used 0 0 here, not 0 1. Okay, so beware of that, should be 0 0 1. So they are trying to use 7.5 and 6.5. In this case, it should be 5.5. So there is a minute error there. Now, so we put the mask. So the mask is in the A, set interrupt mask, enable interrupt mask. Okay, so after enable, we have this interrupt call. So there is the interrupt. Before returning, we need to set the enable interrupt back, because every time we use an interrupt, the interrupt is going to disable itself, so we're going to enable it back before we return. Okay, now these are all hardware controlled mask or interrupt. It's maskable, meaning that you can program it by a software. So this is actually hardware control, but you can program it by your software. It only gonna take it 6 T state, and it's a voltage signal, meaning that if you have MTK85 board, there would be switcher. So you already mask 7.5 and your 7.5 is on, but only if you press a button that's been mapped, then only the interrupts gonna work. Okay, now we have software control interrupt, where it's gonna take 12 T state, and it depends on the code execution. It doesn't need any voltage or anything. Now we have RST0 till RST7. The equivalent call is just the same. So RST5 times by 8 is equivalent to 40. So 40 is equivalent to 16 times 2 plus by 8, which will be 28. So 28. So we have kept. We're going to do the same mathematical stuff, but with a binary code. Okay, so we need to enable it. If we need to enable it, we technically we don't need to enable, but if you want to enable, we need to use this binary code. This binary code translate to 1 1 x x x 1 1 1. So what does the x stands for? If we are trying to use 5 is equivalent to 1 0 1 in binary, so it's gonna be 1 0 1. So our binary code will be 1 1 1 1 1 1 0 1 1 1 1. So the triple digit here 1 0 1 translates into 5. So RST5 just as state. Okay, so we have the hex code, we have the call location, we have the binary code. So technically you could just use the call location, or if you want to use the binary code, you could use the binary code as well. So in order to do that, you could use the same stuff. Just you don't need to put the set interrupt mask or enable interrupt. You could just directly mention this or directly jump to the call. Maybe you could put that org here, jump here, then you could just say in the code jump to the specified interrupt. You don't need to put the set enable or enable mask. Set enable and enable mask is only needed for hardware control, whereas software control is only being controlled by the code execution, and there are RST0 till RST7, which is in this format. Okay, thank you.